Dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about photoelectricity. Photoelectricity can be defined as production of electrons by electromagnetic radiations. It is the emission of electrons from the surface of some metals when light or electromagnetic waves of certain frequency fall on it. We'll learn about critical frequency, critical wavelength, work function, and we'll learn about how Einstein managed to explain it. So let's get started. Wave-particle duality. Okay. Photoelectric effect or photoelectricity. What's meant by photoelectric effect? It is emission of electrons from some metals when irradiated with electromagnetic radiations of sufficiently high frequency. Let me say the definition once again. It is emission of electrons from the surface of some metals when irradiated with electromagnetic radiations, when electromagnetic radiations fall on the surface of these metals. But these radiations should have sufficiently high frequency. So you should focus on this expression, sufficiently high frequency, okay? As a matter of fact, Einstein tackled the photoelectric effect, tackled photoelectricity in 1905. He saw that all experimental laws could be explained if it was assumed that atoms can only absorb light energy in discrete energy packets. Okay? Atoms can only absorb light energy in discrete energy packets. We call it quanta or photons. Light quanta are called photons. Photons are indivisible. So each photon gives all its energy to one electron. Once again, light quanta are called photons. Photons are indivisible, so each photon gives all its energy to one electron. Einstein showed that the energy per photon, your attention please, energy possessed, by just one photon of the electromagnetic radiation should be at least equal to a certain value, we call it work function, to enable the radiation to extract electrons from the surface of the metal. So Einstein showed that the energy per photon of the electromagnetic radiation should be at least equal to the work function of the metal to eject electrons from it, to extract electrons from it. And when a larger photon, a larger quantum, a quantum with an energy greater than the work function is supplied, what happens? The surplus energy is carried by the electrons as, kinetic energy. So once again, talking about explanation of electricity, and the scientist who managed to explain it is Einstein, and he won Nobel Prize for this. So Einstein explanation of photoelectric effect. First of all, if the photon energy is determined from the expression h nu. H is Planck's constant, nu is the frequency of the photon, frequency of the incident radiation. if the photon energy is equal to the work function. This is one possibility. Okay, work function is EW, which is equal to H nu C. Nu C is the threshold frequency or cutoff frequency or critical frequency. If the photon energy is equal to the work function of the metal, what happens? The photon energy is just sufficient, okay, to eject an electron, but the kinetic energy of the freed electron is then 0. Okay, so electrons are ejected, but kinetic energy of the electrons is equal to 0. This happens when the energy of the incident photon is equal to the work function of the metal. Your attention, please. What about the expression known as work function? There is an expression I just mentioned. It is called work function. What about it? It is the minimum quantity of energy. This is the definition of work function. It is the minimum quantity of energy required to emit, required to extract an electron from a given metal surface by just one photon, by a single photon, not by the energy of the, not by the total energy of the radiation. Okay, so it is the minimum quantity of energy required to emit an electron from a given metal surface by a single photon. So each photon should possess this minimum energy so as to eject an electron from the surface of the metal. If the photon energy is greater, this is the second possibility. Photon energy h nu is greater than the work function. The electron is freed, okay, is extracted, and the energy difference between energy of the photon and work function is carried by the electron as kinetic energy. H nu, energy of the photon, minus work function equals half mv squared. Half mv squared is the kinetic energy of the emitted electron. So we can say h nu minus h nu c. Nu c is the threshold frequency, cutoff frequency, critical frequency. They are all the same. It is the minimum frequency required for this phenomenon to take place is equal to half mv squared. So h is taken as common factor, nu minus nu c equals half mv squared. So critical frequency for a given metal is constant. So it's quite easy to, deduce something here. Kinetic energy of the emitted electrons depends only on the frequency of the incident radiation, where V is the maximum velocity of the photoelectron. Photoelectron means the electron emitted by photons, by electromagnetic radiation, and m is its mass. Okay, nu is the frequency of radiation. Nu c is the threshold frequency or critical frequency, and EW is the work function. And the final possibility is if the photon energy is less than the work function, the electron will not be freed at all, no matter how intense the radiation is, no matter how intense the light is. We've got some facts concerning photoelectricity. So talking about facts about photoelectric effects. For any metal, electrons are only emitted if the frequency of the incident light is above some threshold value, is above nu c. So weak ultraviolet has high frequency. So weak ultraviolet can emit electrons from zinc, whereas very intense infrared cannot. Even though it is delivering far more energy per second to each unit area of zinc surface. Okay. What about the threshold frequency, the critical frequency, the cutoff frequency? The threshold frequency depends on the metal. Okay, the maximum kinetic energy of the ejected electrons, and I've just mentioned it, depends on the frequency of the incident light. This is very important piece of information. It is a fact that kinetic energy of the emitted electrons depend on the frequency of the incident radiation, not the intensity of the incident radiation, and is proportional to the difference between the light frequency nu and the threshold frequency. So kinetic energy, maximum kinetic energy of the freed electrons, freed photoelectrons, is proportional to the difference between nu and threshold frequency, nu c. And what about the definition of threshold frequency or cutoff frequency? It is the lowest frequency of an electromagnetic radiation needed to eject electrons from the surface of a certain metal. Let me say it again. It is the lowest frequency of an electromagnetic radiation needed to eject electrons from the surface of a certain metal. Okay, now we've got questions and we want to answer them together. What is the photoelectric effect? What is photoelectricity? It is ejection of electrons of some metals by light of certain frequency. Your attention, there's something important here. Certain frequency. Frequency, yes, is very crucial for this phenomenon to take place. Okay, it won't occur, it won't take place if the frequency falls to a certain limit. So once again, photoelectricity, it is ejection of electrons from the surface of some metals when these metals are, irradiated by light of certain frequency. Why does blue light eject electrons from a certain photosensitive surface, whereas red light has no effect on that surface? So we've got a question now. We've got a photosensitive surface, and blue light is allowed to fall on it. Then red is allowed to fall on this surface. But something happened. Blue light managed to extract electrons from this surface, meanwhile red didn't. What is your explanation? Let me say it again. Why does blue light eject electrons from a certain photosensitive surface, whereas red light has no effect on that surface? Simply because blue light has higher frequency, and this means it has more energy per photon. So each blue photon has, higher energy than each, red photon. Blue light has higher frequency, and this means it has more energy per photon. Another question will bright blue light eject more electrons. Bright blue light. What does it mean? Bright blue light. Bright means, yes, has high intensity. High intensity means we've got many photons. Will bright blue light eject more electrons from a certain photosensitive surface than dim light of the same frequency? Dim blue light. Okay, of course. Yes, because bright blue light has more photons than dim blue light. Another question, and this is very important, it is about the fact. In the photoelectric effect, does brightness means intensity. Intensity has to do with the number of photons. Does brightness or frequency determine the kinetic energy of the ejected electrons? Let me say the question again. In the photoelectric effect, does brightness or frequency determine the kinetic energy of the ejected electrons? Of course, it is frequency. Frequency determines the kinetic energy, whereas brightness is the intensity, determines the number of the ejected electrons. Another question, does the photoelectric effect support the particle model or the wave model of light? This is a very important question. Does the photoelectric effect support the particle model or wave model? Okay, of course, it supports the particle model. It supports the particle model. In a photoelectric emission, okay, your attention, we've got very important question. In a photoelectric emission experiment, a metal surface in an evacuated tube was illuminated with monochromatic light of frequency greater than the threshold frequency. This means the incident radiation is capable of ejecting electrons. Why? Okay, since frequency of the incident radiation is greater than the threshold frequency for such a metal. Okay, if the experiment is repeated with light of the same frequency, same wavelength, but of twice the intensity, yes, we made just one difference. We increased the intensity. What effect will this have on the photon energy? What effect will this have on the photon energy? The maximum kinetic energy of the photoelectron, the work function of the metal. Okay, we'll take them. And finally, the photoelectron current intensity. Photoelectron current intensity. Intensity of the photoelectrons emitted. We'll take it one by one. Photon energy will not change, simply because it depends on the frequency of the incident radiation. And we didn't change, we didn't alter this frequency. We changed only the intensity. So energy of the photon remains unchanged. And what about the kinetic energy of the photoelectrons emitted? We said it depends only on frequency. And frequency is not a change, so it will not change. Maximum kinetic energy of photoelectrons depends on, frequency, not intensity, so it will not be changed. And what about the work function? Work function, it changes when we change the photosensitive surface, the metal itself. We still work on the same metal, so also it didn't change. And finally, what about the intensity of yes, photoelectric current? It will be increased, because when we increase intensity of the incident radiation, we are increasing the number of, yes, incident photons. And since each photon is capable of ejecting electron, so the number of electrons ejected will be increased. Another question: a metal surface is illuminated with monochromatic radiation whose frequency is greater than the threshold frequency. Explain how to increase the number of photoelectrons emitted per second, the maximum kinetic energy of the photoelectrons. First of all, by increasing the intensity of the incident radiation, we'll increase, yes, the number of the emitted electrons. To increase kinetic energy, we have to replace the light with another one, but having higher frequency. Okay, thank you very much. The following table illustrates the response of some metals when exposed to different frequencies of electromagnetic radiation. Okay, we've got a metal, then the metal is exposed to ultraviolet, then blue, and finally, eventually red. Okay, the first was zinc. Ultraviolet managed to extract electrons from it, but blue didn't. Red, of course, did not. Sodium, what about it? Ultraviolet managed to extract electrons from it. Blue also managed to extract electrons from the surface of sodium, but red didn't. And cesium. Yes, ultraviolet managed, blue managed, and red managed. So it was quite easy with the cesium, and this means something here. Okay, which metal has the greatest work function? It is the hardest to extract electrons from it. Yes, it is zinc. Thank you very much. And which one had the highest threshold frequency? Threshold frequency, yes, by multiplying it with a constant, Planck's constant, it will give work function. So it is the same answer. It is zinc. Which metal had the longest threshold wavelength? Of course, it is cesium. And which metal had the least work function? It is the easiest to extract electrons from it. It is cesium, of course. Another type of questions. What's meant by work function of a photosensitive surface is 4 times 10 to the power of negative 19 joule. Work function of a photosensitive surface is 4 times 10 to the power of negative 19. What's meant by work function? Okay, the minimum quantity of energy required to extract an electron, minimum quantity of energy required to extract an electron from this metal, this photosensitive surface, by a single photon of an electromagnetic radiation is 4 times 10 to the power of negative 19 joule. Okay. What's meant by threshold frequency of sodium equals 5.6 times 10 to the power of negative. What's meant by threshold frequency of sodium equals 5.6 times 10 to the power of 14 hertz. Okay. The lowest frequency of an electromagnetic radiation under which the photoelectric effect for sodium does not occur is 5.6 times 10 to the power of 14 hertz. We can say it in a simple way. Okay. The electromagnetic radiation which has frequency lower than 5.6 times 10 power 14 is unable to extract the electromagnetic radiation which has frequency lower than 5.6 times 10 to the power of 14 hertz is unable to extract electrons from the surface of sodium. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.